There's a small chance I'm thinking of going to competition
Okay,
for formula.
okay, cool.
Is there any chance I could take the final early?
The final,
Because is the final that 20th?
I believe so. I need to double
Wednesday?
check. Yeah, go ahead and send me an email. We can arrange something.
Yeah, so it should be the, or 18th? Should be that Wednesday, right?
Okay, yeah, I think so.
I think I'd be leaving that Wednesday.
Okay, yeah, maybe we can have you take it a day or two early. So just send me an email. We can arrange something.
But yeah, it's cool, right? Like,
Yeah, that's fine.
thank you.
Mhm.
Oh, it's like, yeah, it's still good too.
You go.
So if you you go.
Why do we?
Well, I mean, Karen, Brian, and Shaden are going.
Well, definitely.
Yeah, like very well.
Yeah.
Well, I know lady would. Is, so. Across the US, 3. Oh, it's a bit. It's probably 3,000. Yeah, what's next after this? Oh, yeah, they're driving with them. I think they're driving with them there and then flying back. Yeah. But I know if they're flying back, it could be a.
Oh, yeah.
We could fly there and drive back. So, you should save us some money.
Small drivers.
Yeah, I mean, I'm sure we would not drive through the night. It doesn't stop. It's an option. I just want to keep my option open, but if he's cool with it, James, open. I was thinking of flying out there. My grandma lives in Kentucky, so I'd fly from Michigan to Kentucky and see her. I haven't seen her since she moved out there.
More sensitive.
Yeah, exactly. Yeah.
So, yeah. It was had to put up. That's been like pressure down even more than expected.
I supported for 2 classes, which is just nice to get that finance. So it's a little better for me versus like, because when you get to more than 30.
I served. No.
This is a 360. Oh, yeah.
Yeah. After like 30. No.
She's in here with that.
Oh, is
I
she
mean,
really
like,
I did actually be decent. I guess she says pretty fast. I don't know what's the
second. I think I was doing that for. It's like I didn't get it first one. So it's like I don't even want my first one to play. But it's, even then I got like 47.
Okay, no problem. It's good. Just need to.
You guys.
What's the name of the class? The electrical simulation class, is that a graduate level class?
No, it's a tech collective. It's 442.
442.
Yeah. So it's offered in the spring currently.
Spring.
Yeah. So I teach the finite element class, and so that's gonna be 410 in the fall. I teach 417, which is computational heat transfer, and 442, which is computational cardiovascular engineering.
Are you gonna be teaching 410?
Yes.
Okay.
Hey guys. Okay, it's 2:30, so let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good, hang in there. All right, it's 4:20, so stay safe. That's all I can say. So Monday's our midterm. And so, oh yeah, so this morning I recorded the review video, and so it's on YouTube. I just haven't linked it on the website yet. And so I closed the poll this morning and I looked at the winners, and it was, so the review video focused on heat exchangers and internal convection. So those are the two most requested ones. So I'll post that for you guys after I get back to my office after class. Okay, and so the plan for today is we're going to continue our set of lecture notes on radiation. And so last time we just kind of introduced what radiation was, and today we're going to dive a little bit deeper into. All right, and so are there any questions I can answer before we get started today? Okay, all right, so let's go ahead and get started, and let's continue on with introduction to radiation. Okay, so the idea with radiation is that radiation is our third form of heat transfer, right? So we've gone through conduction, we've gone through convection. Radiation is form number 3. And what we saw last time was that radiation was very different. And so as opposed to relying on some kind of material medium, radiation doesn't require that at all. Oh, question. So for the final, I mentioned a sheet for all the constants in different scenarios you have made in the past. Are you still going to share that? Yeah, it's been on the website. Actually, let me show you that right now. Actually, I can show you that real quick. So if you go, yeah, I call it the convection summary handout, and so it's I think most people find it pretty useful. My name and password. Just did this like 2 minutes ago. Right, so if you go to Canvas, you go to our course website, and I don't have it this week, but I had it last week. But I think the easiest way to find it is if you go to Files, you go to Lecture Notes, and then it's Lecture Notes 09A. And so if you click on this, this is a document that shows kind of everything that you need to know with it. So this is kind of a good summary for that. Okay? And so kind of summarizes the convection problem-solving methodology. Here's all your Nusselt number, correlations, Reynolds number, film temperature, mixed boundary layer stuff, okay? Flow over cylinder. So this kind of summarizes everything, and it's formatted in kind of a nice way, so you don't have to hunt everything down. Yeah. And I just added this last year, but last year I forgot to add in stuff for free convection on a horizontal plate, but I added that this year, or last year, I should say. And there's your Nusselt correlations for that. Okay. And so I think the easiest way is to just go to lecture notes and just click on that. Okay. Okay, so let me go ahead and stop sharing. Yep. Come back here. Okay, radiation. And so what we saw last time was radiation was heat transfer that occurs through electromagnetic waves. Okay. And so it doesn't require any medium at all. And in fact, it doesn't even require any kind of atoms or molecules, right? And so it's heat that travels through, through light, basically. And so, everything that you understand about optics, even if you haven't taken optics in a class before, or don't really, know anything technical with it, everything that you kind of understand about how light works, right? So from like flashlights to the sun to even just the lights in this room, right? A lot of that intuition will serve you well in terms of how you can understand radiation, because mechanically they're the same thing. Okay. And so one other thing we went over last time was the fact that every object, as long as it has a non-zero temperature, will emit radiation. Okay. And so visually it looks something like this. So we have an object and it's going to emit radiation all around it in all directions. Okay? And this goes for every single object. Okay? And what we saw last time was that we can quantify this. And so what we found, or what we listed out, was a formula for the emissive power. Okay? And so this is how much radiation, or how much radiation an object will emit. Okay? And so we define this as big E. We say that big E is equal to epsilon times sigma times the surface temperature of the object raised to the 4th power. Okay, and so we define this epsilon here. This is the emissivity. Okay. The sigma here, this is the Stefan-Boltzmann constant. And Ts, this is simply the surface temperature of the object. And remember, with radiation, before previously, it didn't really matter whether we put our temperatures in degrees Celsius or Kelvin, right? But for radiation, it does matter, because since we're raising the temperature to the 4th power, it's going to make a big difference whether you use Celsius or Kelvin. And so the correct one to use here is Kelvin. Okay, so make sure that whenever you're doing radiation, you convert all temperatures to Kelvin. Okay, and so last time what we did was we talked quite a bit about emissivity, what that meant, and we talked about irradiation and absorption and transmittance and everything like that. And so what I wanted to start with today was an example that kind of shows you, how all of these things kind of work in practice. Okay? Okay, so before I do the example, are there any questions on any of this? This is a recap from last time. Okay, all right, so let's look at an example just to see. It's a very simple example, but I think it's good to do. Okay, and so let's consider this hot pipe. And this hot pipe is going to be sitting within a room. Very exciting, I know. Okay, so here is our pipe. Let's say that the surface temperature of the pipe is 200 degrees C. And this pipe has a diameter of 70 millimeters. Okay. And this is sitting in a room. Okay. And let's say that the room is at a temperature of 25 degrees C. And so we'll say that T surrounding is equal to 25 degrees C. Okay. Okay. And so before we put any numbers on this, let's just talk about the situation intuitively, right? And so we have a pipe here that's very hot. So 200 degrees C is extremely hot, and it's inside a room which is at room temperature, right? And so just intuitively, right, we can see that when you have a very hot object and relatively cool surroundings, then heat is going to escape from the pipe, right? And so that we understand. But for this problem, what we want to say is how much heat is this pipe going to lose via radiation? Oh, let me just say that the pipe, we'll just for simplicity, we'll say the pipe has a length of 1 meter. Okay. Okay. All right. And so what we know for the pipe the pipe is going to have a emissive power of epsilon sigma times Ts to the fourth. Okay. Oh, I forgot to mention. So the pipe also has an emissivity of 0.8. Okay. So that's usually going to be given to you in the problem because that's kind of material dependent. Okay. And so all we have to do is just kind of plug into this. Okay. But this pipe is actually going to be, it's not just emitting power, but it's emitting that power to the surroundings. Okay. So the surroundings are also going to be emitting heat. Right. And so the surroundings, we can also say, it's giving off this much radiation as well, okay? And what we can say is that this radiation from the surroundings is hitting onto the pipe as well, okay? And so for this particular example, because we're kind of focusing on just the pipe, we're going to assume that the emissivity is kind of the same on both sides, okay? And so the total amount of heat loss is just kind of the difference between how much radiation the pipe itself is giving off minus the amount of heat that is taking in from the environment. Okay? Okay. And so if we quantify that, so we call that Q loss, okay, this is equal to epsilon sigma is going to be the same on both terms. So we have Ts to the fourth minus T surroundings to the fourth as well, okay? But we have to be careful here because the problem asks for heat loss, right? And so let's kind of remind ourselves what the units for E are, right? So the units for E are the same as heat flux. And so this is a watt per meter square. Okay, watt per meter square. And so in order to get Q, what we have to do is we have to multiply this Q loss by area, okay? And that area is actually going to be the surface area of the pipe because that's the surface that's interacting with the environment. And so a final formula for Q loss is going to be epsilon sigma times Ts to the fourth minus T surroundings to the fourth, okay, multiplied by the surface area of the pipe. So the surface area of the pipe is going to be pi times the diameter times the length, right? So it's the perimeter of the pipe multiplied by the length. And we'll ignore the caps of the pipe. Okay. All right, so we have everything here. And so epsilon we know is 0.8. The Boltzmann constant, what was that again? The Boltzmann constant is 5.67 times 10 to the minus 8. Okay. Ts, we know Ts is 200 degrees C. But remember, we have to convert this to Kelvin, and so we have to add 273. Okay. And T surrounding is going to be 25 plus 273. Remember, don't forget to convert to Kelvin. Okay, and then we have pi and the diameter. The diameter is, I think, 70 millimeters, so 7 centimeters, and the length is 1 meter. And so we plug everything in, and we get a radiation heat loss of 420 watts. How fitting. I didn't plan that, by the way. That's just kind of how it happened. Okay, and so we can see that you have this really hot pipe right here, and we have this amount of heat loss, right? Let's compare this. And so remember what we talked about last time is that we said that radiation is only really significant when you have very, very high temperatures. Let's compare the situation. And so let's say that inside this room, let's say that we turn on a fan. Okay. And so as we turn on a fan, it's going to create some convection across the pipe surface. Okay. And that convection, we'll say, has a convection coefficient of 15. Okay. And so with this H, let's compute how much convection heat loss do we get from the surface. And so 15 is fairly mild, and so it's not a, it's not a lot of convection, but it's enough to cause something. And so let's compare the amount of convection heat loss that we get compared to radiation. And so we have Q convection. And of course, we have our Newton's law of cooling here. So we have H times A times Ts minus T surrounding. Right, the A is the same, so the A is going to be the surface area of the pipe. Ts and T surrounding here, we can just leave them as at their degrees Celsius. Okay, we have H from right there. And we plug it in, we get 577 watts. Okay. Okay. And so even with a very modest amount of convection, you can see here that we actually get more heat loss due to that convection. Okay. And so, this kind of gives you some numbers to it, right? So remember last time we said that most of the time you're going to neglect radiation, except in very unique situations. Here, I would say we have one of those situations. So 200 degrees C is extremely, extremely hot. And so even when you have an extremely hot object, even a modest amount of convection can still kind of overpower, right? They're on the same ballpark, don't get me wrong. It's not like you can ignore radiation here. But we had to crank the temperature all the way up to 200, before we saw anything, that approaches convection. Okay, and so for most applications, you can ignore convection, and that's kind of why we save it to the end of the class. But it's important to think about what situations where radiation is going to be relevant. All right, any questions on this example here? Okay. Okay, so let's move on to the next topic, which is radiation intensity. Okay, and so the last example that we did was actually very unique because if you look at the geometry, we have a pipe that's completely enclosed within a room, right? So what we're saying is that everything, all the radiation that leaves the pipe is going to be caught by the room, or it's going to hit the room. And consequently too, so because the room is kind of completely surrounding the pipe, all the radiation that the room emits is going to be caught by the pipe as well, okay? That doesn't necessarily happen all the time. And so first, let me start by saying that when radiation leaves the surface, it goes out equally in all directions. Okay. And so if we have an object here, right? Right? Another way that you can say this is that radiation doesn't really have a preferred direction. So it just kind of just, goes every direction that it can, right? Okay. And so that's great. And so if you have a specific geometry where the geometry can catch all of these radiation rays, then you can basically perform the analysis as we just did. Okay. But that doesn't happen all the time. And so let's say that there's another object. Okay. And so let's say we have another object right here. Okay, another object. And this other object has a finite amount of size, right? It's not going to be fully, fully engulfing it. And so what we can, because this object is kind of offset to the side and it's not fully surrounding it, only a small amount of these radiation rays are going to hit that object, right? And so, probably these two, would hit the object, but everything outside of this, those are either just going to go around the object or just not even head in its general direction. Okay. And so when we compute, the emissive power, of epsilon sigma ts to the fourth, we can't really say that all of that is going to reach the other object, right? And so, now geometry is going to play a much bigger role, because we have to account for this factor. Okay. And so what we're going to do is we're going to go through kind of an exercise in determining how you can actually determine this. Okay. Does that make sense about why this factor comes to be? Okay. And so the reason this section is called radiation intensity is that we have this formula for emissive power right here. But it doesn't really, it's not a good, I would say it's not a good metric for kind of practical computation of the radiation, because it's good to find out how much raw radiation is an object giving off, but what you're more interested in is how much of that is actually being passed to another object. Okay? And so instead, it's better to put things in terms of intensity, where you can kind of account for the geometry a little bit easier. Okay, so let me, before we move any further, let's go ahead and do a change of coordinates. Okay. And so because radiation has this property where it kind of goes out equally in all directions, kind of the most natural way to describe this is to use spherical coordinates. Okay. Because if you think about what a sphere looks like, right? A sphere, if we define it, right, and we have the center right there, right? One way that we can think of the sphere is that every point along the surface of the sphere is equidistant to the center of the sphere, right? So that's what it means to be a sphere. Right? And so that's kind of a good mindset to think about with radiation, because if you stand a certain distance away from the object that's radiating heat, right? you're going to feel a different amount of radiation, whether you step forward towards the object or step away from it, okay? And so this kind of raw distance or shortest distance between the object and you know, is a good way to kind of describe radiation, okay? Okay. And so, you know, from here on out, we're going to be talking in spherical coordinates. Okay. Next, we have to introduce this idea of the solid angle. Okay. And so a solid angle is kind of like the three-dimensional equivalent of a regular angle, okay? And so what it does is that it kind of relates, you know, in spherical coordinates, this kind of concept of an angle and the area that it covers, okay? That's a very poor definition, but but let me kind of draw a picture just to kind of remind you, just to kind of show you, okay? And so let's do 2D first. So I think everyone kind of understands the concept of an angle, right? Okay. And so here I have an acute angle. And so this angle, you know, or this arrangement, we know has an angle of theta, right? And that theta kind of describes how close or how far our two lines are, right? Right. That's kind of how we loosely define what an angle is, right? And so, you know, a smaller angle means that the two lines are, you know, closer together, and a bigger angle means that they're farther apart. Okay? One other way that this angle, one other way that we can use this angle is by computing an arc length, right? And so if we say that this angle right here is part of a circle, right? What we can say is that this angle here, it subtends an arc like that, okay? Okay. And in particular, you know, when we think of arc length, you know, the arc length, you know, I'll give it the symbol S, will be equal to the radius of the circle multiplied by the angle, right? Right, that's how we compute arc length. And so, you know, one way that you can think of arc length is that if you stay basically a fixed distance, if you stay a fixed distance away from the center of a circle and you walk, you know, within a certain angle, the arc length is the distance that you travel. Okay? And so we can say is that arc length describes the distance you travel when staying okay, so when staying a fixed distance from the center and you walk, you know, by an angle of theta. Okay. right? And so the angle and the arc length kind of have this relationship, right? And so, angle, we all intuitively know what an angle is, but it has this relationship to an arc length based on the radius of that circle. Okay. The solid angle is basically a three-dimensional kind of analog to the same thing, right? And so, the analog to kind of this kind of slice of pizza right here would be like a flashlight beam. Okay. And so that's how I like to think of solid angle, right? And so a flashlight beam might look something like this. And so we might have a cone, but at the end of the cone, we have an area, right? And so what we can say is that this flashlight beam has an outer area. We'll call that a DAN. Okay. And just like the circle, we'll say that the distance, where this is the center here from the origin, right? The area, what that represents is the area that's covered, when you're a fixed distance away from the center, when you go across a solid angle of omega. Okay. And so the solid angle, it's really hard to draw in a two-dimensional thing right here, but it's kind of what represents this, this area right here. Okay. And typically we give the solid angle a symbol of omega. Okay. All right, and so we can come up with kind of an analogous definition for solid angle, kind of based on our definition of angle above, right? And so solid angle, it describes this relationship between the area that's subtended by the solid angle if you stay a fixed distance away from the center. Okay. Okay. And so think of that analogy of a flashlight. Right? So I think a flashlight is kind of the best analogy for this, because you know that when we shine a flashlight into a dark room, right? And say I'm shining the flashlight on that wall back there, and I'm right here, it paints a certain area, right? Because I'm standing a fixed distance away from the wall, and the flashlight has a fixed solid angle, right? But intuitively, you know that if I walk closer to that wall, right? And so I'm keeping the flashlight at the same level, and I'm walking closer to the wall. What do you expect the spotlight to do? It's going to decrease, right? Because my distance to the wall is getting shorter, right? Versus if I back up, right? If I back up from the wall, then the spotlight's going to get bigger, right? Because the solid angle is staying the same, but the distance is changing, right? And so the relationship between the area and the solid angle is given by the following. So what we can say is that the solid angle, omega, is equal to the area that it subtends divided by the radius squared. And so if you look at the units for this value here, right? So area has units of length squared, R has units of length, and so they're going to cancel out. And so just like an angle, right? An angle doesn't really have units. Solid angle also doesn't have any units, but it does have to have a name, right? And so for angles, we say that it has units of like degrees or radians. For solid angles, what we say is that their units are called steradians, which is not a real unit, but it's it's useful for describing. I think it's kind of a silly name, but They had to call it something, I guess. Okay. And another way that we can put this, and so this is kind of the you know the classical definition for solid angle, but for the purposes of the derivation that we're going to do, we're going to put this in differential form. And so we're going to say that d omega is equal to dan divided by r squared. Question?
Is this related to the inverse square law?
I would have to look up what the inverse square law is again too.
I guess like well, it's kind of like the flashlight. The further you are, the farther you get, the more area is covered by that beam.
Yeah, I would say so. I mean, that's basically kind of the same. That's a good analogy for this. But we're going to use the solid angle kind of in a radiation kind of way. But yeah, the same idea as that. Okay. Any questions on this so far? Yeah.
Can you go over what it's in differential?
Oh, I mean, so differential, when we put an equation in differential form, you know, I put a d in front. All this means is that it's a tiny version. Yeah. So it's infinitesimally small and infinitesimally small thing. It's because, you know, we're going to put this in derivatives and integrals, and it just kind of helps with that. Okay, so let's go ahead and move on. And so let's kind of bring this back to radiation, right? And so let's apply this concept to you know, the radiation that gets emitted from a surface. Okay. All right, so let's say that we have a surface here, and so it's going to lay flat on a table. And this surface is going to be emitting radiation. And so let me go ahead and put some spherical coordinates on this. And so, you know, let's put a vertical axis here, okay? Horizontal axis here. Okay. And so remember, in spherical coordinates, we have two angles. Okay? And so first we have the polar angle, and so the polar angle describes, you know, how our rotation in the xy plane, and so we'll give that the symbol phi. Okay. And we also have the azimuthal angle. So the azimuthal angle kind of tells you how much you rotate from the vertical axis, and so we'll call that theta right there. Okay, and so we're going to ignore kind of the bottom half because, you know, we know that this object is going to radiate in all directions, but let's just consider all the radiation that happens above this object. Okay, and so what we can do is we can draw a hemisphere, right, or you know, half a sphere around this object. Actually, I'm going to use a different color for it. And so I put this dome around an object. You know, what we can say is that everything within this, on the surface of this dome, is kind of equidistant from the object. Okay. And so on this dome, I'm going to cut out kind of a small slice. And so let's say that we cut a small slice right here. Okay. Right. So that's just a small slice of the dome, and we'll call this DA, because it's a small area. All right. And so if we take the corners of this slice and we trace it back to the origin, you know, it might look something like this. Okay. And so based on the spherical coordinates, let's say that it's a distance r. Okay. And so based on this, based on spherical coordinates, let's compute what the area is of this slice. Okay. And so we can say that dA is equal to r d theta, okay? And so you can think of that as the arc length of the in the azimuthal direction that the area subtends, okay? And we're going to multiply that by the arc length in the opposite direction, in the polar direction. Okay? And so that's going to be r sine theta d phi. Okay. And so we go ahead and evaluate this. We get dA is equal to r squared sine theta d theta d phi. Okay. Right. So here d theta and d phi kind of represent the angles on which the area is being drawn by, right? Okay, so let's go. So now that we have this area right here, let's use this area to compute the solid angle that this this patch kind of subtends. Okay, and so we scroll back up here, we can see that the solid angle is just simply equal to the area divided by r squared. Okay, and so what we can say is that d omega is equal to dA divided by r squared. Okay, and so this r squared is going to cancel out with the r squared that's in dA, and so what we get is that d omega is equal to sine theta d theta d phi. Okay. Okay, so now we have the solid angle, right? And so that's good. And so the idea behind this and the idea behind intensity is that, you know, if we're this patch, or if we're sitting on this patch, right, we want to find out how much of the emitted energy from our surface passes through this patch. Okay. All right. And so to do that, you know, we have to do a bit more geometry. Okay. So let me take this image here and let me kind of view it just from the side. Okay. And so, you know, kind of keep your eye on this surface here, right? So remember, you know, we have two surfaces. Whoa. Right. We have two surfaces. And so we have the one that's on the table here. And so this is our emitting surface. Okay. And our patch here, this is our absorbing surface, right? So that's the one that's going to catch the radiation. Okay. Okay. And so what I'm going to do is I'm going to take this, take the emitting surface, and instead of kind of viewing it from the top, I'm going to view it from the side now. Okay. And so this line right here, this is now our emitting surfaces, but we're viewing it from the side. And similarly, if we draw kind of the side view of the patch, you know, it might look something like this. Okay. So this here is our dA. Okay, so let me go ahead and draw this too. And so since we're viewing it from the side, we can view the azimuthal angle. Okay. And if we draw kind of a dotted line here, we can say that this theta here represents that azimuthal angle. Okay. Okay. All right, so imagine, imagine that you're sitting on the surface dA, okay? Okay. You're sitting on dA and you want to look at the emitting surface, right? So you want to look kind of directly at it, okay? The size of the emitting surface or how big that surface is depends on the angle in which you're looking at it. Okay. Right, so that's kind of a fancy way of just kind of, I think, something that we all kind of understand. Right? And so if I took this pen, right? And so if you view the pen from this angle, it looks very long, right? But if I view it kind of straight down the barrel, it looks a lot smaller because I'm looking at it from a different angle, right? And so depending on the angle at which you view things, it's going to appear different because what your eyes kind of naturally do is that it takes three-dimensional objects and it projects kind of a two-dimensional image based on that, right? It's like it's as if you took a picture of it, right? And so the angle at which you take the picture is going to change what the object looks like, right? And so as an example, let's say that we change this azimuthal angle, and so let's say we change it to 0, okay? And so in other words, you're going to view the emitting surface from kind of straight above. Okay? Okay. And so if you view the object from straight above, of course it's going to look really big, right? So take a piece of paper that's in front of you, right? And so kind of angle yourself so that you're looking right on top of it. The piece of paper looks bigger, right? But if you try to view the paper from the side, right? And so if you set the azimuthal angle to like pi/2, right? Then it's going to look really thin because you're looking at it from the side. Okay. Thus, what we can say is that, based on the area or based on kind of what angle that we're looking at for the patch, the effective area of the emitting surface is going to be different. Okay. All right. And so we can go ahead and quantify that with an equation. Okay. And so we quantify that with an equation. We're going to take basically the effective area. Okay. We'll call this dA effective. Okay. That's going to be the cosine of theta, okay, multiplied by the solid angle. And so we plug in our expression for solid angle back up here. We can say that dA effective is going to be cosine theta, sine theta, d theta, d phi. Okay. Because that's important because, the more of the emitting surface that you see, the more the radiation that you're going to be exposed to, right? And so if you don't really see as much of the emitting surface, what's the question? Oh, d phi. Yeah. Yeah, the other angle, the polar angle. Yeah. And so if you can't really see, or if the surface can't really see you, then you're not going to be experiencing much of the radiation. Okay? And so basically, the more surface area that you see, the more the more the radiation is going to affect you. Okay. Any questions on this so far? it's a lot of geometry, I know, you know, it's even kind of hard for me to follow sometimes too. But okay, let's go ahead and relate this back to heat transfer, okay? And so let's kind of take this in mind, right? And let's kind of relate it back to the fact that, you know, we know that every object is going to emit radiation, okay? And so, you know, we can compute the kind of the raw amount of heat that the object is that an object's putting out by multiplying the surface area of the object multiplied by its emissive power. Okay. Okay. And so this is just the emitting surface now. And so this has nothing to do with the patch, right? And so for the emitting surface, what we can say is that if we take the emissive power, you know, that's the emissivity, Stefan-Boltzmann constant, surface area raised to the fourth, and we multiply by the surface area of that object, okay? And so we'll call that A1, and that's the total amount of heat transfer. Okay? Okay. Because of the way radiation works, because it kind of spreads equally in all directions, you know, what we can say is that this energy or this power is going to be spread across that entire hemisphere. Okay. And so as you get further away from the object, you expect the radiation to be less intense, right? Just because it's covering a much larger area, right? So let's go back to our flashlight analogy, like from before, right? And so if you shine a flashlight at a wall and you walk closer to it, right, the light beam is going to get smaller, but it's also going to get a lot more bright, right? But if you stand farther away, right, the light beam is going to get bigger, but it's going to be less bright, okay? Because there's this idea of intensity that, you know, the further away you are from the object, the less intense it's going to be. Right, so let's quantify this fact. And so let's define a new quantity. And so let's define intensity, right? And so we define intensity to be the emissive power of an object divided by the surface area of the hemisphere around it. Okay? So we have I for intensity is equal to E, which is the emissive power divided by the area of the hemisphere. Okay. And so if we solve this expression for E, then what we get is E is equal to I times A hemisphere. Okay. So let's take this expression for E, because this is a little bit of a better expression for E because it accounts for the intensity and the area of the hemisphere, right? And so let's go ahead and plug it back into this expression right here. Okay, and so if we do that, we get Q, which is the amount of energy that we, or the raw amount of power that we receive from radiation as the intensity multiplied by A1 multiplied by area of the hemisphere. So we just did quite a few steps in kind of a short amount of time. So let me go ahead and label this. So this I here is intensity. This A1, this A1 is the surface area of the emitting object. Okay. And this A hemisphere is the surface area of the hemisphere that goes around the object. Okay. And this hemisphere is not anything physical. It's something that we can kind of draw around the object. Okay. So what this is saying is that, if we have our object here, and we have a big hemisphere, right? Right? Pretend that it's center, okay, that I can draw, right? And so, if we kind of sum up all the energy that's around this hemisphere, we're going to get that amount right there, okay? But, if we make this hemisphere smaller, right? Right, and so let's say that we make the hemisphere kind of much smaller like this, okay? Then we're gonna experience a different amount of heat transfer, okay? Different amount of intensity. Okay. And so we've hopped around quite a bit like this, but we're gonna take this expression here and then focus on this one, because most of the time, we're not interested in computing the emission to an entire hemisphere, but just kind of a small patch, right? And so what we're going to do is that we're going to take this expression for the patch that we have up here, okay, and then plug that in for this, and then perform an integration in order to get what we need. Okay. So it's kind of a long-winded derivation. It's not the easiest to follow, I know, but I kind of tried to do my best with analogies throughout. And so let me pause here for a second. So are there any questions on this so far? Okay. All right, so let's go ahead and just finish this up. And so most of the time, we're not interested in the entire hemisphere, but only just a small part. Okay. And so instead of multiplying that by a hemisphere, what we can do is we can instead multiply it by the effective area of a patch. Okay. Okay. And so instead of a hemisphere, which is the entire hemisphere, what we can do instead is convert this to omega, which is our solid angle of the patch, multiplied by the viewing correction. Right? And so remember, depending on where you are on the sphere, you're going to see a different amount of the object. Okay? And so we quantify that by omega cosine theta. And so finally, if we plug that in, we can finally determine the heat transfer from an emitting surface to a small patch. Okay, and so if we substitute this in, we have Q is equal to omega times the intensity multiplied by the emitting area times cosine of theta. All right, and so what this represents is the heat transfer from surface A1 to a patch of size omega, okay, with viewing correction cosine theta. A very long-winded explanation for a formula, but I think that kind of sums it up pretty nicely. Okay. All right, and so next I have a couple examples for you, just to kind of show you how this is used in practice. And after those examples, I think we'll probably wrap it up for today. Okay, so any questions on this formula here? Okay. All right, so let's go ahead and do an example. Okay, so for this example, let's say that we have a small surface that's emitting radiation. Okay. Its area, let's say its area is equal to 10 to the minus 3 meters square. Okay. And let's say that its intensity is 7,000 watts per meter square. Watts per meter square. Okay. And so what we say is that the radiation from this surface is being intercepted by two other surfaces. Okay. Okay, so we'll call them A2 and A3. Okay. All right, and so visually it looks something like this. And so we have A1. Okay. All right, we'll say that A2 is directly above it. Okay. And A3 is right here. Okay. All right. And so we'll assume that all the panels here, all the patches have the same area. So A2, A3 will also equal 10 to the minus 3 meters square. Okay. Let's compute the distance between them. And so we'll assume the distance here is 0.5 meters. We'll say that A2 is directly above A1. Meanwhile, A3 has an azimuthal angle of 45 degrees. Okay. Okay. And so what are we after here? And so let's say that we want to compute. First of all, let's compute the solid angles subtended by A2 and A3. And two, let's compute the rate at which radiation is intercepted by A2 and A3. Okay. All right, so there's our example setup here. Okay. Any questions on this? Okay. All right, so let's start with the solid angles. And so solid angles for both of these are actually going to be the same. Okay. So remember, the way that we compute solid angles is we do omega is equal to the area of the intercepting surface, and so this can be A2 or A3, And we're going to divide by the distance between them and the emitting surface squared, okay? And so since A2 and A3 here are the same, and so, we're going to get the same solid angle. And so this is going to be 10 to the minus 3 meters square divided by 0.5 meters square. Okay. Okay. And so you punch that into your calculator and you get 4 times 10 to the minus 3 steradians. Steradians is such a silly word. I always giggle whenever I say it. Okay, so that's fairly straightforward, right? And so we have a formula for solid angle, and we just punch it in, right? And so basically, the bigger the intercepting surfaces are, so if A2 or A3 are bigger, then of course that's going to result in a bigger solid angle, right? And also, if they were closer, if R was smaller, then that's going to increase the solid angle as well. Okay, so remember, think of the flashlight analogy. Okay. And so now that the solid angles are computed, let's go ahead and plug that in for Q in this expression right here, okay? And so we have Q, we know it's equal to omega I times cosine of theta times A1. Okay. And so let's do this for A2 first. And so A2, even though both surfaces here have the same solid angle, they have different polar angles, right? So A2 here is directly above. And so what we can say is that theta is equal to 0. Okay. Okay. And so if we do that, we have omega, which is 4 times 10 to the minus 3. Okay. The intensity here is 7,000 watts per meter square. Okay. We have cosine of theta, and so if theta is 0, we have cosine of 0, which is just 1. Okay. And then we're going to multiply by A1. And so A1 here is 10 to the minus 3 meters square. Okay. And so we plug all that in, what we get is 28 times 10 to the minus 3 watts. For A3, it's going to be similar, except for the theta angle for A3 is not 0, but it's 45 degrees. Okay. And so we're just going to plug into the exact same formula. The only thing that changes here is this term right here. Okay. So instead of cosine of 0, we have cosine 45. Cosine 45 is root 2 over 2. Okay. And so we do that, we get Q is equal to 19.8 times 10 to the minus 3 watts. Okay. So fairly straightforward. So kind of long derivations, but simple formulas. Yeah. Let's see. So the meters here is going to cancel out with these meters, and that's how we get the watts right there. This omega is so the omega units is steradians, and so steradians is kind of like radians, and so it's kind of like a fake unit. Yeah, we just kind of ignore it. Yeah. So it's just like degrees or radians or things like that. Yeah. Okay. Any questions on this? Okay. All right. So for the last example for today, let's throw just kind of a small twist on this. Okay. And so if you look at this example up here, right? If you look at A2 and A3, both of them are facing, or they're turned in a certain way such that they're facing A1 to the best of its ability, right? What if we have an intercepting surface that's not turned exactly like that? And so in other words, what if we had a situation like this where we had kind of a vertical surface like this, okay? if we were to draw kind of the shortest distance between the emitting surface, so let's see here, this is A1, this is a new surface, A4, right? And so that line right there represents kind of the shortest distance between A4 and A1, right? For the previous two examples, you know, the intercepting surfaces were turned such that it faces that, okay? But this one's not the case. And so, you know, this one's kind of rotated a bit such that you have an angle right here. So we'll call this theta 2, okay? And so how does that affect our calculations? And so where this affects our calculations is that it primarily affects the solid angle. Right? Because now that we're not fully turned towards our emitting surface, then our solid angle here is going to be a little bit smaller, okay? And so the way that we account for that is that our omega now is going to be A, so we'll say A4 divided by R squared cosine of theta 2, okay? And so when you're not fully turned towards your emitting surface, your solid angle is going to be decreased by an amount of cosine theta 2, okay? Okay. And so, you know, at this point, I want to pause and just say that, you know, it's a lot of angles to keep track of. And so, you know, we're in spherical coordinates, so there's a lot of angles there. And I'm kind of throwing a new one into you here. And so, you know, just kind of be really careful about all your angles and just kind of know what each of them represent. Okay? All right, so very quickly, let's do a quick example. And so let's do that same scenario above. Okay? Right, and so let's say that the polar angle for this surface is 60 degrees. And this theta right here, theta 2, we'll say that this is 30 degrees. Okay. But A4 has the same area, so it's going to be 10 to the minus 3 meters squared. Okay. Okay, and so if we assume the same properties for A1, and so A1 is 10 to the minus 3 meters squared, I is 7,000 watts per meter square. Okay. Let's compute Q in this instance. All right, so the first thing we're going to compute is the solid angle. And so the solid angle for this is going to be A4 divided by R squared. Oh, the R here is 0.5, same as before. Okay. Times cosine of the amount that we're turning away from our emitting surface. So this will be cosine of 30. Okay. And so we do that, we get a solid angle of 3.46 times 10 to the minus 3 steradians. Okay. Now that we have the new solid angle, we can just go ahead and plug that in for Q. So we have Q is equal to omega I cosine of theta times A1. Okay. Where here our theta value is different, right? And so our theta value for the previous one was 45, but now our azimuthal angle here is 60, right? And so we're going to plug in 60 degrees for this. Okay. But everything else will stay the same. And so we get a Q of 12.1 times 10 to the minus 3 watts. Okay. All right, and so that's kind of just a small adjustment that you have to make when you're not fully turned towards your surface. Okay. Question? That's just what's given in this problem. And so in the previous problem, the other surface was oriented 45 degrees. Here we kind of just moved it down a little bit. And so this, and so when I say theta, I mean this angle right here. Yeah. Okay. So theta, so 30 is the angle that we're turned away. 60 is kind of the angle, 60 you can think of the angle that we're on the hemisphere around. Yeah, so 60 is the polar angle, azimuthal angle. All right, any final questions before we wrap it up for today? Okay. Our question, so can I explain again what the purpose of the hemisphere is? Let me answer that after class, because it's a little bit of a long-winded. Okay, and so if you want to stick around for that answer, you can stick around. But if not, thank you guys for tuning in today. Remember, Monday is the exam, so please make sure you come in person on Monday. I won't be on Zoom on Monday, so please make sure you're there. I'll post a review video when I get back to my office. And if you have any questions when you're studying, just please let me know. Right. So have a great weekend, everyone. Best of luck studying, and I'll see you all on Monday. All right, Ken. So the purpose of the hemisphere, the whole idea with the hemisphere is that it represents kind of a region which is equidistant away from the surface. Right. Remember, when we first started, we said that we're working in spherical coordinates because for radiation, that's kind of what makes sense, right? And so this hemisphere, what we say is that everything on this hemisphere everything on the hemisphere is equidistant away from our emitting surface. Right. And so when we plug into the formula, right? And so when we plug into this formula down here, right, this Q formula, what we're saying is that the amount of Q that you experience, depends on kind of where you are in the hemisphere and how much area of that hemisphere that you're taking up, right? And so that's kind of encapsulated by the solid angle. And so instead of this formula up here, where we say the Q is equal to the I times the A times the area of the entire hemisphere, right? Usually instead you don't have that entire hemisphere. And so you replace that hemisphere with the solid angle. Yeah. Does that make a bit more sense?
Yeah, I got it. Thank you.
Kang, are you there? Okay, great. Yeah, it's a bit confusing, I know, but we can talk about it more in office hours.
Yeah, thank you, Professor.
Okay, that's cute. That's cute.
And I watched Attack on Titan movie.
Oh yeah.
And it inspired me to organize notes into episodes.
Okay, yeah, no, that's good. Yeah, I mean, absolutely. That's easy.
Are you caught with the?
No. So I watched Attack on Titan, the first episode. I saw Aaron's mom got eaten. Oh man, this is too brutal. I didn't want to watch anymore. I heard it's very good.
It's really worth
It's
it.
very
Yeah.
good.
I was gonna stop my first self today.
Yeah. Yeah, that was very graphic.
Wait, but you spoiled it to people that didn't watch the first episode. Oh no.
Wait, what?
You spoiled it to people that didn't watch the first
Oh, it's
episode.
okay. It's the first episode. Yep.
The first question you covered, I was wondering how you
Oh yeah, it was just given in the problem. I just forgot to give it. So
Oh,
yeah, so yeah, right. So for that, that's a property of the surface. So that has to be given.
Okay.
There's no way to for you to do it.
I was looking through it, I didn't see anything.
Yeah, I just forgot to give
Okay,
it.
so it was.
Yeah.
And I'm assuming you added 270 to convert it to color.
Exactly.
Okay, got it.